This section explains redox reactions, what happens in your cell, how you can take an iron 3+ and it can turn to iron 2+, why people want to keep flour white, what about rust on boats, and why the Statue of Liberty does not rust. Oxidation number is where we start. It's the charge on an atom. And I'm going to leave this to you. How would you go about determining the charge on chromium in this potassium chromate ionic compound? Well, let's talk about rusting. Rusting is the corrosion of iron, and iron is Fe2O3. Iron is in the +3 oxidation state. It has lost, well, it first lost 2, but then it lost 1 more electron, and that happens to metals. The O2- ion, that is oxygen that has gained 2 electrons, and that happens to nonmetals. So you know about the charges from chapter 2. Now let's delve a little deeper and explain things. I want to say that it's a hypothetical charge. When you look at rust, there's no indication that you can see the number +3. All right, oxidation number rules. The first rule says if you have an element in its elemental form, it will have an oxidation number of 0. Things like sodium and iron, the diatomic molecules, and also some of the less well-known and nonmetals have an oxidation number of 0. The second is if you have a monoatomic ion, it's going to be the same as its charge. So pull out a periodic table and see where these things are, and you can, in your mind, set +1, +2, +3, +4. Those are for the metals. Go to the other side and look at the nonmetals. Look at the halogens, look at the oxygen group and the nitrogen group. Those are those common oxidation numbers that you memorized back in chapter 2. Now we're going to use them in chapter 4. As far as the transition metals, they have many oxidation states. They are left until chemistry 1220. And hydrogen tends to be a +1 when it's bonded to nonmetals. That's what you will encounter in our class. So an oxidation number has a sign, and the sign is normally written before the number, but I've noticed things changing. So this is probably the most important. If we have a species, if we have something like water, if we have something like an ion, I've devised a little way to help students get through this. Let's do water first. Water has absolutely no charge. Oxygen, I know, is a -2, and there's only 1 oxygen. Hydrogen is a +1, and since there are 2, it is a +2. +2 and -2 are going to be equal to 0. Let's say someone wants you to tell them the oxidation state of scandium. Well, if I look at the material, it has an overall charge of 0. I know chlorines are -1 to make it a -3. It says that this must have the same +3 charge, as we all know aluminum has a +3 charge. Let's move down here to these ions. If we were in class, I'd be writing them all on the board. Now we have a -2 charge on this ion. We know that every oxygen is a -2. -2 times 7 gives us a -14. What can we add to a -14 to give us a -2? That has to be a +12. So I would place a +12 here. I see there are 2 ions, and that says that each one is a +6. Again, you'll see something like this on a midterm. The other one I want to do here has to do with the sulfate ion. It is a -2. If I look at oxygen, it's a -2 times 4 is a -8. Sulfur must be a +6 to balance. Say, how can we have sulfur in a +6 oxidation state? Well, it is sitting in the cation slot. That out, and you're... So now that you've seen how to assign oxidation numbers, let's talk about redox. Redox is one reactant is reduced while one reactant is oxidized. That's where the terminology comes from, redox. Reduction is the gain of electrons. They occur as one of the reactants. Oxidation is the loss of electrons. They occur as the products. So we'll explain where this comes from, but for now, let's give zinc a 0. Zinc nitrate is a +2. What we've seen is that zinc has gone from a 0 to a +2 oxidation state. That is called oxidation. And oxidation, remember, is the loss of electrons. Copper, on the other hand, has gone from a +2 to a 0. That process is called reduction. And you can see we have the half reaction written here. where we're adding the two electrons. So that in a nutshell is a redox reaction. Now, two other things to notice. There is something called a reducing agent, and the agent actually undergoes oxidation. What undergoes oxidation in this example? Zinc. The oxidizing agent, it undergoes reduction. And what is the agent doing that? It would be the copper nitrate. Copper 2+ is undergoing reduction. But if I'm talking about the agent, I must talk about the entire species. Notice all of these labels are put on reactants. They're never put on products, but on your exam, sometimes products are options. Don't fall for that trick, okay? So let's get a little bit deeper. In order to understand what's going on, people ran reactions. These two reactions, one had a copper metal with an iron 2+ solution. The other one had a copper 2+ solution with an iron metal. When people did the reaction, what they found is the first one had absolutely no reaction. What they saw was reaction with the second solution, and I stole the picture out of chapter 20 on electrochem where we go into more detail. So what you'll be expected to do is to predict the products of the molecular reaction. I'll show you how. And then take that reaction and turn it into a net ionic reaction by removing the spectator ions. So what I've done is I've written the net ionic, but I've also taken time to write the individual half reactions, the reduction and the oxidation. Notice when I write them that the electrons are going to drop out, and the reaction that I get from the two reactions matches the net ionic reaction. Now this is for copper and iron, but there are many, 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 many different matchups, okay? So how did people figure out what was going on? Well, they ran experiments, and when they mixed magnesium and hydrochloric acid, or I like to joke, drop acid, what they found was hydrogen gas. Maybe they threw a match in and it exploded. And they also found the presence of magnesium chloride in solution. So imagine this experiment was run, the next experiment was run, where they took aqueous silver nitrate and they added copper. And when they did that, what they found was silver as a solid was being plated out. And they also saw the beautiful blue color of copper nitrate. So again, it's by observation and it is by experiment. Experiments where you can make some observations. They compiled all of this in this table called an activity series that is always provided for working the problems. Notice I've said here, the higher element is always oxidized. Students often struggle with this, so let's do some examples. Magnesium versus hydrogen. I'm going to find magnesium on the chart. I'm going to find hydrogen. Oh, it's sort of buried as hydrogen the molecule and hydrogen the acid, but there it sits. Magnesium is higher. It is going to be oxidized. If you can turn off your device and take a look at copper versus silver. Try to make a prediction. So I'm going to say, here's copper, here's silver. They are very close together. But copper is above silver and it is going to be oxidized. Finally, turn your device off again and look for zinc versus copper. You see zinc is above. It will be oxidized. So again, you may be asked a question which is as simple as this, where you have to say which element is oxidized, or you may be given a chemical equation. So practice. Potassium sits definitely above. Potassium can make a +1. Water is a +1. It goes to a 0. And you'd have to see this at least once to know what's going on. Potassium will form potassium hydroxide, and we will also form hydrogen gas. And I've put their numbers, below them. What happened in terms of oxidation number? Potassium went from 0 to +1. It was oxidized. Hydrogen went from +1 to 0. It is undergoing reduction. You may be asked also to provide a balanced chemical equation, and you do that by inspection. Okay, so that's one metal with usually water. Here we have the same metal and we're dropping acid. In each case, it is a halogen acid. Both of them are sources of H+. Zinc sits above the acid, so I'll be making some zinc 2+. I will have some halogens sitting around. I'm designating that by an X. That's how we designate halogens. And we will also make some hydrogen gas. So please note, as long as you have a halogen equal to bromine, chlorine, iodide, fluorine, this would be the reaction you would see. So it's going to take a little bit of insight in order to decide what's going on. Now, my last example to point out, notice it is couples. Copper with iron 2+ and iron with copper 2+. What you would do is you would see which one is above. But let's make another note. If we look at these two materials, Fe2+, it is already oxidized. So rather than even hunting around, you can say this one has absolutely no reaction. Now, I did not plan well, but I'll write it down here. What we would make is FeSO4 aqueous, and we would produce copper solid. Please practice. There are homeworks plenty for you to work with. Make sure you can understand it.